Uh, Thank you, Mike and Elise. I'm going to talk to you about soil moisture dynamics under automated irrigation in Utah. And it was on a farm. And so the issue is drought. We know drought is becoming more prevalent. And so in trying to address this issue, we are trying to find the ways of more economically managing the water that we use on crops. And also the farmers in the area that we are studying use mostly surface irrigation. And as we know, surface irrigation is also associated with deep percolation. And associated with that, we have soil nutrients that are also used because of the deep percolation. So we carried out this study on farmers that adopted a modified type of surface irrigation called sedge irrigation. And in this case, it's called automated sedge irrigation. And so we were comparing normal surface irrigation for conventional surface irrigation and automated sedge irrigation in terms of how they affect soil moisture within the root zone. So that's what we were basically working on. Yeah, so that is the background that I was only talking about. So we want to try and address the issues of depercolation and nutrient losses. And also the other important thing that we did this study, unlike most studies in the area, which are based on like research farms and controlled plots, this was actually a on-farm trial where farmers are actually doing their production without any interference. So we tried to link soil moisture dynamics and irrigation. That's the other importance of this study. So the automated sedge irrigation that I mentioned is just where farmers apply water in pulses or in sedges within one dike. They use different dikes. So they apply water maybe halfway, then they go to another dike, just like I hope it's showing in that diagram how the water is applied. And it's also automated. That's the other difference from conventional irrigation. Yeah. So the problem again is of loss of nutrients through depercolation. And in this case, we want to try and to see how automated sedge irrigation improves or shapes the soil moisture movement within the soil profile as compared to conventional irrigation, which I call here CSI. Right. So we just wanted to understand how does continuous soil moisture monitoring review soil moisture behavior within the soil in different depths and across the field for automated sedge irrigation and the normal irrigation. And also, how does soil moisture monitoring tell us about the irrigation, how the irrigation is performing in our field? And the other one, the other question that we wanted to answer was, does sedge irrigation really reduce the deep percolation losses associated with surface irrigation? So those were three key questions that we wanted to answer. So this study was carried out in an area that is very close to the northern shore of the Great Lakes, of the Great Salt Lake in Utah. So this soil, I mean, this place is very sensitive to nutrient loads because the nutrients will go directly into the lake. So that's why we chose that area there. And it was in an on-farm trial on a second year alfalfa crop. And basically it was on one field. It was a case study where we installed volumetric sensors, soil moisture sensors at 5 depths, 15 centimeters up to 150 centimeters in depth. So we installed those sensors at the head end of the field, middle section of the field, and at the tail end of the field. So as to try and cover the whole field. So we quantified the amount of water that was introduced to the root zone by irrigation. So we simply were taking measurements of volumetric soil moisture and noting the difference between the moisture just before irrigation and at the peak of irrigation. So multiplying that by the layer of soil profile that we are looking at, we could determine the change in storage. That change in storage will be equivalent to the amount of water that has been introduced by irrigation within that layer, right? So I'll go straight to the irrigation parameters that we were looking at. We're looking at soil water storage uniformity. How uniform is the soil moisture across the field and in different depths because of these different types of irrigation. So we were using DU, normally it's called distribution uniformity. So in this case, we're simply looking at the area of the field, be it the head or the tail or the middle, which has minimum water amount that has been added to the soil as compared to the mean of the whole field. So that was our distribution uniformity parameter. We also looked at coefficient of variation. How variable is the amount of moisture that has been introduced into the soil by the irrigation? So we have these interpretation parameters for CV and DU. Um, let me see if I can try and... Okay, so anyway, we also tried to look at the comparison of the head end of the field and the tail end of the field, how the moisture is is being distributed. So we had to use a head to tail ratio to do that. So I'll go straight to the results. The time series of the soil moisture are what we recorded throughout the years from 2023 to 2025. And this one is a 15 centimeter depth time series for 3 sensors. One we located in the head section, which is the blue one, and the green one was in the tail section. The orange one was in the middle section. So we could actually see the oscillations of soil moisture. And from this, we can actually pick the irrigation events. So we identified in this case, for example, 7 irrigation events that we then characterized in our studies. We identified through the soil moisture, but of course, we then validated it with the farmer records. So this is the 2024 whole year soil moisture. In Utah, we can't farm in winter. It will be there will be snow, so they normally farm right now until the end of October. So here again, you can identify the irrigation events in this stage. So I also put in here the deeper soil sensors like the 105 centimeters and the 150 centimeters. The key thing to say here is that at the deeper levels, especially in the tail end, the sensors were not reacting to any of the irrigations. For example, this green one here, the soil, it means the soil was almost always saturated in the tail end. All right. So then I'll go on to the storage response. Right. So the results that we got when we analyzed this, the DU changed from 69% before when the farmer was using conventional irrigation in 2023, and it improved to 86% by 2025, which means that the uniformity of irrigation was actually improved a lot by introducing automated sedge irrigation. And the coefficient of variation improved from 27% to 14%. So the lower the number for coefficient of variation, it means that the better the uniformity of irrigation, right? The other key result that came out of there is that on the soil surface, the soil layer, the uniformity was the same for both normal irrigation and the RC or automated sedge irrigation. But in the deeper levels, that's where most of the changes in uniformity happened. The uniformity was improved very much by RC in the lower levels of the soil, as this chart can show here. For example, the first 30 centimeters, the 0 to 30 centimeters layer, you can see the DU for 2023, 2024, and 25 were basically the same. But if you go deeper at 30 centimeters to 60 centimeters, you can see it improved from 51% with conventional irrigation to 85%, but when you are now talking about automated sedge irrigation, the same story here for the 60 to 90 centimeters, but the lowest level, the deepest level, there wasn't much change there. So in the tail section water deficit, we also noticed that for conventional surface irrigation, the tail end of the field received 6.1% more moisture or more water than the rest of the field. In 2024 and 2025, it actually received less water than the rest of the field. So the other aspect was the drainage risk, which is the risk of water percolating deeper than the root zone. So when we found out that in 2023, for every irrigation that was applied, about 0.43 inches of water was lost in the deeper than the root zone in the tail end of the field. But by 2024, I can't see the 2025 year, but basically there was very little to no deep percolation of moisture in the lower ends, in the tail end of the field when we were using automated sedge irrigation. So the key takeaway points here are that RC or automated sedge irrigation may reduce deep percolation losses and nutrient leaching, while at the same time improving uniformity of irrigation along the field and also in different layers of the root zone. The other thing is that since it reduces deep percolation losses, it may reduce return flows from agricultural land and also what we call non-consumptive use of water. And the other conclusion is that, or takeaway message is that soil moisture monitoring may actually review a soil profile processes that we cannot actually record accurately with normal irrigation assessment or evaluation protocols that we use. For example, you can actually dissect the whole profile and see different uniformity layers depending on the soil layer. That's why you can do that with soil moisture, but with standard irrigation evaluation protocols, that may be difficult to do. Yes. Thank you very much for listening, and I take questions.
Do we have questions? John?
Yeah, great talk. Thanks so much. So question, how important is the soil characterization in your approach for characterizing the soil moisture profile, and what's the potential for scaling this approach to a larger field?
Okay, if I got the questions well, is that how important is soil characterization in measuring soil moisture, and how can we scale this up? Yes. So in this study, we actually did a physical characterization, texture analysis of the soil, but I didn't include it in here. But the way we also determined field capacity in all the layers of the soil, in the field head end, middle end, and tail section, so that we identified a particular field capacity for each particular type of field. So we're comparing all these to a particular field capacity of that particular section of the field. So that is very important to characterize the soil. And scalability, I think scalability, once we identify this, we do this in different soil types, we can basically then scale it up. We can then tell certain patterns. If we have like a release curve, for example, for each particular soil, we can then easily scale it up. I think it can be scalable. Yes. Yeah.
One more back there.
Yeah. Cool talk. In certain places in Montana, we found that flood irrigation can help to recharge groundwater systems and support late season stream flows.
Yes.
In vulnerable places with ecological consequences.
Yes.
I know in this case you don't want to promote deep percolation because you're trying to keep leaching it to a minimum, but could this method be modified to support maybe the intention of trying to recharge groundwater systems and actually encourage deep percolation.
Okay, so the question was that with this approach, we are trying to minimize deep percolation, but can this be modified to encourage a deep percolation? Yes, I would say yes, because when you study the soil moisture levels, you can actually apply your irrigation based on off of what you want to achieve. Do you want deep percolation losses or do you want to minimize? In this case, because we are so close to the Great Salt Lake, we want to minimize the percolation losses because nutrients will leach into the Great Salt Lake. Yes. Okay.
All right, thank you, Ngoni.
Okay, thank you very much.